First of all, thank you for joining me today, because we are all tired probably already, and we all wait for a beer at the reception. Me too. So I would like to finish on time, no worries. And today I would like to give you some kind of alternative view on how we build enterprise software, some alternative to the architectures that we know today and that we use today. And I think I could actually win the contest for the longest presentation title. So the topic for today is pushing enterprise software to the next level, self-contained web applications on in-memory platforms. And before I introduce myself, I would like to ask you 3 questions. So, who heard about self-contained systems architecture before? Anybody? That's good. So that's what I expected. So then I don't really need to ask second question, which is who used them in production? Because I think nobody. It's even better, because I think this basic introduction will be good for you. And then now I have some kind of scary question also. Who does some front-end development? Okay, that's good. Not too much, but no worries. I'm not going to talk about front-end only, but I will just touch this topic a little bit, because it's important from the whole perspective. Okay, so my name is Michał Nosek. I am a software and sales engineer at StarCounter. And StarCounter is a Swedish company that is building a future of enterprise software. We aim to revolutionize how the enterprise software is built, how it's deployed, and how it's distributed and how it's sold. And we do all of this leveraging our own in-memory technology, in-memory application platform that we built ourselves. And you can find me on GitHub. You can find me, of course, on LinkedIn. You can also write an email to me, so I can answer your question and do some introduction if you like. So what's on today's agenda? Well, first of all, I would like to have a quick look at the enterprise software architectures of today, what are challenges and what are the actual problems with that. Then I would like to introduce 3 technology areas or ingredients that we are going to mix today to show this new approach that we would like to promote. So first ingredient is RAM memory and in-memory technology. Then it's a modern web platform that evolved recently a lot. And last but not least, it's self-contained system architecture. And after this, in the second part, I'm going to introduce StarCounter in-memory application platform, how the platform architecture looks like, how the single application built according to this architecture that I will present looks like. I will also have some small demo of the simple application, some code and actual application that is running. Then I will talk a little bit about integration, because this is a big challenge if we have system built out of multiple pieces. And also a little bit, if we will have time, about the future, how we look at it, how it will evolve soon thanks to the hardware development. So when we build a big system, a bigger application, a portal or something to support any kind of business case that has a user interface, you have to decide how many things you want to build first. In the past, it often happened to be one thing, the often criticized monolith. It's a common understanding now that monoliths cause troubles and should be really avoided at all costs. Some of the problems that we see is very long builds, bad maintainability, lock into specific technologies, also huge effort to change something. It's such monolith. And therefore, we have a longer time to market and many more. So currently, of course, microservices are talk of the town. But also microservices, they don't come without the costs, as we know. So if you really have microservices doing one thing, even sometimes implemented in approximately 100 lines of code, as stated by some people, you will have a lot of them, and things like network traffic, resilience, more complex implementation compared to just calling methods in the monolith, monitoring, coordination, consistency, all these have to be handled, which is not easy. So it also grows. Another thing that I think it's true about enterprise software of today is described in the computing adage that is called Wirths Law, which states that software is getting slower more rapidly than hardware becomes faster. And I think you can agree with me. So it was named by Niklaus Wirth and then restated and attributed to Larry Page, founder of Google. It's known as Wirths Law, Page's Law, Gates' Law, whatever other name you can attach to it. But what I really like is like these two forms. And first is what Intel giveth, Microsoft taketh away, or what Andy giveth, Bill taketh away. And this is a challenge of the enterprise software today that we all try to solve. That's why we are here at In-Memory Computing Summit, because it basically gives us more performance, right? So now I would like to introduce these three technology areas that I mentioned before. And first is RAM memory. So what about RAM memory? First thing is RAM prices, because like over time, memory is getting cheaper and cheaper. So it allows us to use memory for other things that only critical for CPU operations, like for instance databases that we do more and more. The same trend with the prices is related not only to hardware, but also to the availability of memory in cloud services, in virtual machines that we can get in the cloud. So today on Azure or AWS, it's nothing special that we can get more than 10 terabytes of RAM memory on a single virtual machine. And these big machines are also cheaper and cheaper over time. But if we analyze actually this diagram, and especially like the last part of it, if we zoom in here, it's not that obvious that RAM memory is getting cheaper. It's actually the opposite. So different sources actually show that in like last 2 years, memory price raised a little bit. So probably we're hitting a wall with the current DRAM technology. And to actually make these prices lower, we need to look for some alternative. But we'll be back to that a little bit later. What RAM means for the databases itself? So, well, databases evolved from conventional, how I call it, approach, where the main memory was disk, and everything was written to the disk, and everything was read from disk. Of course, there was some cache in memory or indexes that we keep in memory, but we all know that this is suboptimal approach, and it's not very efficient, especially today as we have more RAM. So this evolved into in-memory database, but there is no really big difference because storage, like main storage, was moved to the RAM memory, but still to actually provide persistence, we are capped by disk, and like usually all operations are written to the log to the disk, which is usually slow. So the more writes we have, the bigger performance problem we got. But also, here is the problem. The problem is between the applications, different applications, especially distributed applications, and the database, if we have especially centralized database. So this is why performance really suffer, because we have to access database very often, and things like serialization, deserialization, communication, transferring data that takes a lot of our performance. So as a result, it doesn't matter that much anymore how fast our storage is and our RAM memory is, because we cannot really access it faster. And the latency is something that we cannot really remove from that architecture. So regarding RAM memory, it's still getting faster. With the next generation of memory, it's better utilized by modern CPUs, especially new multi-core CPUs. But what is bad about RAM memory? Well, communication with this memory and the storage that is in that memory is not getting faster anymore, and we cannot really overcome latency. This memory is still not durable, meaning that we need to use some persistent storage. Of course, there are like approaches like Intel and VM, but we'll be back to that a little bit later. So, second technology piece that we are going to use today is a modern web platform. But again, don't worry, we will not talk too much about that. Recently, web developed more rapidly than ever. It becomes, or web applications becomes more reactive, more real-time, more composable because of multiple standards that were introduced to the web platform. And important standards that I would like to highlight and mention here is Shadow DOM that allows to combine different DOM trees separately into one document in the browser. Custom elements that allows to create encapsulated elements for the front end, for the web. And also WebSockets that are already quite widely used. So they allow to communicate with web applications in the real time, very fast and very efficiently. And over and over, web tries to actually do encapsulation and assimilation in the right way, which is good. But if we sum up things about the web, it's possible to run web applications basically everywhere. You can probably run the browser on your fridge if you like, if you have a modern fridge, I guess. So it's the same process and the same platform for all kinds of devices that you can use. It's also easy for the developers to get nice look and feel and well-organized, rich content, which is different than in the native platforms. They don't really give that to you because, well, CSS and HTML, they're really good at it. And modularity is a priority. It's easy to load different elements from different sources to our web application. But on the cons side, it's still not implemented everywhere in the same way. So we have like the different engines, different versions that interpret our code in a different ways. So that makes development harder. Encapsulation is still not ideal because global scope still exists. And it's easy to pollute this global scope as we combine different applications. Also web is online, so it doesn't really fit very well for offline scenarios. Of course, we can have some caching, but usually it means troubles. So we should rather avoid that with web. And the last part of the technology that I think is very important is self-contained systems architecture. And this is quite a new concept in the enterprise software. It's not yet very popular. It's a different view on the architecture that I will explain in a moment. And it's described and promoted by companies like, for instance, InnoQ is a German company. And you can find first mentions in the internet like about 2014, as far as I know. And next 4 slides I actually borrowed from them, and you can find like more details about that architecture on the website that I mentioned here, scsarchitecture.org. So if you like to go deeper with this architecture, you can find it there. So what this self-contained system architecture is about. So if we look at the application as a monolith, it contains numerous different things inside of the single system. It has different domains, user interface, business logic, persistence, modules, components, framework, libraries, multiple things. It's really, really complex. With all these layers and elements in one place, this monolith tends to grow, which is really bad, and that's why we developed some modular architectures, different approaches to that. So if you cut a monolith system along its every domain and wrap every domain into a separate, replaceable web application, then such application can be referred to as a self-contained systems that we're going to talk about today. So every self-contained system is an autonomous web application, meaning that it can run on its own and also deliver some value, some real business value. It does not rely directly on any other systems. It's usually owned by one team because it's small enough to be developed by one team. Communication in such application shouldn't be really synchronous, at least inside the same request-response cycle. It can, of course, have some service API for third-party systems or for native mobile applications. But what's important, it must include both data layer, data, and logic. Optionally, it can have some UI, because not all applications, of course, have UI. Also, business code and business logic shouldn't be shared between the applications, and ideally, shared infrastructure should be minimized. But as in any architecture, it's all about compromises that we make to actually reach our goal and build our system that fulfills requirements that we have. How about integration in such applications? That it's a quite tricky thing. So typically, this integration between self-contained applications is done over systems' web interfaces, so over UI to minimize coupling. So simple hyperlinks can be used to navigate between the systems, and also redirections can be used to ensure that navigation works in both directions. But as you can imagine, such approach is rather suboptimal. It's not very good. So let's look at the pros and cons of such approach. Well, we have modularization, for sure. We have also maintainability, because we have separate systems that we can develop separately. We have quite loose coupling between these systems, because they are integrated over user interfaces usually. But the problem is that integration is sometimes not enough, because we would like to have some integration on the data level as well. It's also really hard to get the same look and feel. You can imagine, as we develop applications separately in the different teams, and all of these applications are full stack applications, there will be always differences between them. So as a user, as you open such system and you click between the different self-contained applications, there is a high chance that it will feel differently. It's not that easy, at least, to provide the same common look and feel. And also, inconsistency on the data level is another challenge that we have to deal with. So now I would like to go to the second part of my presentation. So to address these issues that we have with all these technologies, like with the RAM memory and its prices, with modern web platform, with self-contained system applications, I would like to introduce StarCounter in-memory application platform that is created and developed to build self-contained systems, among others. So what is important here, that it shares some concepts with the ideal self-contained system architecture, but it's kind of interpretation of that, so it's not like one-to-one how it works with the definition. It leverages RAM memory, modern web, And well, I think it fills some gaps between these three and maybe interesting alternative to what we use today for some systems. So let's have a look into general platform architecture. So starting from the bottom, we have in-memory application platform that is responsible for persistence, providing data store that is in memory. It also provides things like queries and API to access data, and some special layer that is called mapping that allows to integrate different data models from different applications, so they behave as a single application. I will present more details a bit later. Then we have application layer that contains, well, business logic, entities are declared there, and also view models that are kind of contracts between the server side and the client side. So what we actually can use into user interface. Then we have communication. Only here between the server side and the client side, which is based on the library called Palindrome. It's an open source library developed by us and also community around that. It uses WebSockets to communicate with the server, so it's very lightweight, and it only sends the deltas between the client side and the server side. So there is no much network traffic between front-end and back-end. Then we also have front-end framework of your choice. It could be React, it could be Polymer, any other framework that can actually provide two-way data binding for the UI. If we compare this traditional stack to StarCounter stack, well, we basically have some persistence layer, but we have no object relational mapper or network connection between the application and the database, because applications are run inside the database on the same machine. Then we have some application code and view models that are representing data for the client side, and then we have network only once to communicate with the clients here. What's also important about the, especially for the people who don't really like to write a lot of code for the front end, that front end is very simple. So it's only about presentation layer, really. It contains no business logic, because usually we write a lot of client-side logic, what we call thick client, and in StarCounter, we rather write thin clients, so we only create presentation layer, and all the rest is provided by the server. So, for instance, if you take form validation, you don't have to write it both on the client side and on the server side, because everything is provided by the server. So it gives a lot easier maintenance, for instance, and of course less code, especially code that is duplicated both on the server and client side. Okay, so let's have a look in the context of self-contained application. Let's have a look how this single app looks like. So first of all, the data storage is in memory database, which persistence provided by disk. So logs and all operations in the database are stored either synchronously or asynchronously on the disk. It's fully ACID compliant, so it provides snapshot isolation for all transactions and different kinds of transactions. There are short and long-running transactions, which have actually different parameters and different uses. And it's also very flexible from the developer perspective. So it's really possible to model any data structure that is possible to model in the object-oriented language. It does not really matter how our entities are modeled, because it all can be stored in-memory database. And what's like the biggest difference from the architecture perspective? Well, this approach is called DBMS, so it's a virtual machine database management system, and it's a patented technology. And basically, the difference is here at the communication between the applications, different applications, and the database. So, well, applications share their memory with the database. So effectively, application heap is replaced by the database heap. So what does it mean? It means that we don't really have communication between the applications and the database, because as we call the constructor, as we create some object in our application, some business entity, it's already persisted, and it's already in the database. So we call constructor, then we create a new object in the database. So when we change some attribute in the object, then it's also changed in the database. And the same with calling some destructors and things like that. So that's why it's replaced by the database heap. Regarding business logic layer, well, it's meant to be polyglot. So right now, platform supports only C#, but it's designed in a way that we would like to introduce another languages to the platform, so we can build different systems, self-contained applications in different languages, and then run them side by side in a single database. Usually there is no special data access layer, so this logic is simplified. It's also platform agnostic because you can run it on Windows and Linux. And thanks to the architecture where the memory is shared between the application and the database, it's really close to the real time. So let's compare traditional application data access to the StarCounter application data access. Well, basically, normally we have some database process where we have a memory that stores our objects. Then we have some network, or in the best case, some inter-process communication and object relational mapper. And then we have copy of the same object in the application. So the more objects we need to operate on, the more data we have to copy from the database. So if you look at StarCounter application, this memory is shared between the database process and the application process. So effectively, all you have in your application is some small, what we call proxy objects. So it actually allows you to, you can look at it as a pointer to the shared memory space. So instead of copying objects from the database to the application, you just operate on these objects directly. And so it's very efficient, and what's also important, it reduces memory footprint a lot. If you calculate all memory that you need to run your application, it's much less actually with this approach, because you don't basically copy. And the same if you have more applications. I will show that later, but multiple applications here, if you multiply these applications, they can still point to the same piece of memory. So even though you have applications that operate on the same objects, you don't copy these objects multiple times as you do in this approach. And regarding the last layer of the self-contained application built on StarCounter, it's web native, as I mentioned before. It communicates usually over WebSocket, even though you can create some other interfaces like REST interface, of course, and also code some interface on raw TCP or UDP protocol. It's also allowed. What's different from the typical self-contained system application is that it's design agnostic, and by this I mean that like developer of the application does not really care that much about how it looks like, because only when you combine multiple applications into one system, then this person, like we call him solution owner, defines what is the final look and feel. And also client is thin, so it's really not too much code to make it work, and I will show that on the demo that I would like to show right now. So I would like to show a little bit of code, but not too much. Well, are you familiar with C#? Or who uses C#? Well, it's not much different than Java, for instance. So this example will be super simple. So I don't think it's a problem. But I would like to. Can you all see the code? Can you read that? So I would like to quickly show how the StarCounter, like super simple StarCounter application looks like. And this, I would like to present to you these 3 layers that I mentioned. So this is a C# console application in my virtual machine. I have a Visual Studio here. So basically, as we have the database class here, it's just like normal C# class. There is nothing special about this class except it's marked with the database attributes. So StarCounter engine knows what should be persisted and what should be omitted from the database perspective, and you can use all the features that C# gives you. So this is how we create database objects and database schema. Actually, this is just your entities that are database schema. And then we have here some simple handler registered, so I can return some page, and this page is run in the long database transaction scope. So I create a person page, and then to this page data attribute, I retrieve using SQL first element from IMCS demo person table. So if you look at this IMCS demo person, it's actually the namespace, like the full name of this class that I declared here. So here is the namespace and class name. So this is the table. Then if we go 1 layer up, we have a view model that actually is bounded to the person object. So as we said, this data attribute in the handler to some person object, it's already connected and bounded with the database. So what we do here is we have some calculated property. So out of the first name and last name, we concatenate these 2, and we get the full name of a person. Also, we have some handlers for the buttons. It's like for the triggers that we have here, and all these methods do is committing transaction or rolling back the transaction. Then to this view model, there is connected what we call JSON by example. So here we define what is visible to the front-end side and to the client. Also with the $sign here, which means that it can be modified from the client side. If there is no $sign here, it's a read-only field that cannot be really changed from the client. And then last part is a super simple HTML form that contains of just native HTML tags here. We have a first name and some input. We have a last name. Then we have 2 buttons. One that will trigger our save handler, and another one that will trigger our cancel handler. And also, then we use this full name calculated property to present like concatenation of these 2 fields. How it looks like in the browser, I'm not going to compile that now because it never works, so I have it all running already. So basically, I open that page that I declared there. I have my form with the first name and last name. It's John Doe. I have save and cancel button and full name that is John Doe here. Also, I opened the web console, so hopefully we can see some patches that are updating the state from the client side to the server side. So basically, as I change this name here, there is a patch going out to the server saying that first name property was changed, and then server recalculates automatically. I mean, first of all, it in the scope of the transaction changes that in the database, but also it recalculates all properties that are based on that. So we have patch coming back that sets this property to John with double N here. And then when I change that, I can change more and refresh the page. It actually disappears because I didn't store the transaction. It was open transaction that we discarded actually because of loading the new page. So what I have to do is to click save to store my transaction, to commit that. Then if I reload, everything is here. So that's like super simple without going into details, self-contained application, StarCounter platform with all layers that I mentioned before. Let's go back to my presentation because now I'd like to talk a little bit about the integration, so how these applications interact together and how they're integrated. So typically, self-contained systems are integrated on the user interface level, but we think that to make the real business system with multiple applications, we need some better integration. So we have integration on both the data level and the user interface level. And on the data level, it's basically, as I mentioned before, we have not only single application that is accessing the database object in the shared memory space, but we can run multiple applications accessing the same object. That reduces memory footprint, and it's very, very efficient approach. But self-contained systems should be built with the separate data models. So different teams code their own data models, and they would like to run them together. It's also important when we take modules from the different vendors, let's say. So for that, we have additional layer that is our secret sauce, I would say, and it's called mapper. So this layer basically deals with the transformation of the data between the different applications that are developed separately. So effectively, every single self-contained system that is run on StarCounter thinks that it deals with its own data model. So, but in fact, it's virtualized. So we store data only once, and this transformation for every application is done in the background. So transformation is going on the fly, and these applications also share the same database transactions. That's why we don't have to care about consistency, because it's all in the same memory space. So this process of doing these transformations from the developer's perspective, it's right now, I would say, semi-automatic, but our goal is to make it as automatic as is possible. So we are doing some machine learning on the different data models to actually learn how developers define their data models, so we can make these transformations for them without engaging developers to that work, because usually integration takes a lot of time. And on the user interface level, that is separate, another layer of integration, we have different applications that contribute with their own user interfaces, own pieces of interface. But then finally, on the same screen, we can mix different pieces of the user interface coming from different applications, which is different to the standard self-contained systems approach. Because we don't show the single application at the time, but we show responses from multiple applications on the screen. So just to show it with a little bit more real example, some kind of demo. So right now on the screen we see I think 3 self-contained StarCounter application. One contributes with this small piece of the interface here, which is actually responsible for signing in the user and dealing with authentication. Then we have another piece of the user interface that is responsible for search across the applications. That's also a separate application that contributes with this user interface piece. Then we have form, like in the CRM system, let's say, that is contributed by some other application to the same screen. And as you run more application, you can just see that there is more information on the same screen coming from different applications that are integrated. So let's say that if two applications, so one from here and one from here, change something in the database, this is all running in the same database transaction. So if I show something here and change there, it will be changed also here, even though it's a separate application, synchronously. And then if we add more applications, well, there we have some other application that shows some events timeline for that specific user, Stephen Fry. It's also a separate application with a different data model. Then we add some application that is responsible for showing images. So it shows the image for this specific user and images for a specific events here. So this is how we can build like a more complex system, adding more applications and extending these systems. If I don't like this application that deals with images because let's say it allows me to upload only single image for the object, I can easily replace only this single application with some more advanced system that is application that's built by someone else. So to summarize this approach, well, comparing to the self-contained systems, we keep modularization, maintainability. We still have quite loose coupling, and we have better integration. We have common look and feel and consistency between these applications. So basically, we removed some problems of the self-contained architecture, but we introduced another problem or issue that you can call, and some kind of platform lock-in, of course. But on the other hand, it's not that bad as you can think about, because first of all, it's as I mentioned, polyglot, so you can write your application in the different languages. You can run it on the different platforms, and multiple parts of the system are open sourced, so it's not like everything closed in a single platform. So I would say that some parts that are like secret sauce are closed, but you can't really hide it that you have some platform login. But this is the trade-off. So about some real-world example, because I think we still have a couple minutes. Well, there are different systems running in production, and one of these systems is called Palma, from a company called Modular Management. And well, this application shortly helps to control production process of different items in a modular way, so you can assemble and optimize different processes in a production. And right now it contains about 20 self-contained applications, and this number is growing. Also one of the, or actually the biggest Swedish retailer runs StarCounter based system with around 26 apps right now, and more to come, because this system is still in development. And maybe a few words about performance. So we of course do different benchmarks. And thanks to this architecture where applications access the data in the database directly, performance is really good, especially in the cases where the ratio of writes and reads is optimal. So because we have to store everything on disk, then the more writes you have, the worse scalability is. But with reads, it scales pretty much linearly, or almost linearly, with CPU threads or cores. Yeah, so here are some numbers also, and some comparison to MariaDB with 5 nodes and Node.js app that are doing money transfer between accounts, super simple application. So some raw numbers are like we reach about 1 million database operations per second, and this Node.js application reached 55,000 of operations per second. How about the future? Because there are like a couple very interesting developments recently in the hardware space, especially, which is non-volatile RAM memory that will be placed somewhere between main system memory and persistent memory, that is disk. We're looking forward to it because then we're not capped by disk anymore on writes. It will be much more efficient, even though it's not that performant. It will be huge step because then we can operate on the data and we don't have to store any logs. And then also recovery time when you restart your server will be much better because data is already there. Also, we work on a new data store that is better optimized. I cannot see all colors here. Anyway, that is more like optimized for analytics as well, not only for typical OLTP workload to have better performance with all typical workloads that we have in the business applications, where we will utilize multi-core CPUs, both volatile and non-volatile memory, and it will be some kind of hybrid column and row-based store. So, to sum up, because we are almost out of time, how the enterprise software of tomorrow will look like, what we think. Well, it will be simplified because we should not actually add more layers or complexity to the software. We should rather try to do the opposite because current technology enables us to do that. Everything will be near real time or real time. Depends what you prefer, but rather near real time. So we expect results here and now with every kind of system, not only some super high performant systems. It will be easier to maintain due to the better modularization. It will be also reusable, not only across the one company, but imagine that you have multiple systems that are like compatible on the same platform. You can run any applications that are integrated automatically. Then you can take different apps from different vendors, run them together and compose your system, not writing that much code, only your small part that is very special for you have to be developed then. It will be fully web-based, or actually it already is very often, and it's all about fast data, reacting here and now, and HTAP or HOPE. It really depends which analytics firm you prefer. And that's it. Thank you. Do you have any questions? Yeah.
So, for example, classic scenario, you mentioned the mapper.
Yeah.
I just saw this recently. Postgres with materialized views, and then you have different apps using different materialized views from the same table. Do you guys currently support using those to kind of generate the integration for your mapper, so that you could maybe get rid of the materialized views and then just use your mapper, or do you support that as like a migration?
Well, so you can actually think about the mapper as a materialized view, actually, yeah, because data is stored once, as in the table, and then you have like a virtualized table that is comparable to that. So implementation is definitely different. So there's no like tool to migrate that.
Oh, okay.
Yeah, you have to like do it from scratch. Let's say that the base of the mapper. So this transformation is we are getting more and more data models into our base, so it's easier to build something even manually right now. But the real goal is to make it automatic, and we are trying to do this materialized view, as you mentioned, truly automatically. So really without any effort from the developer.
So, I don't know, but related to that, because I actually went through the little example app. It looks like there's actually a decent amount of maybe some boilerplate code for things where you can define a save action, but then you actually still have to write the trigger that commits the transaction.
Yeah.
Do you guys have any plans to maybe just generate that, or have something?
Yeah, of course. So there are like different approaches. I mean, some developers prefer more control in some cases, some developers less control, but then write to less boilerplate. So basically you can choose. So for some things, there are like planned really code generators, so you can generate easily, for instance, form based on your database model, and then you don't have to write any logic. That's something that already exists on other platforms. So we also would like to have that, and we also continuously work on making it more developer friendly. So you don't have to write any boilerplate. I mean, not any boilerplate, but there are like also libraries that we built, and also libraries from, if we think about C# and .NET host from ASP.NET, and in the next version ASP.NET Core, because the next version of StarCounter supports ASP.NET Core. So basically then you can run your console application, .NET Core console application, and just include StarCounter and start using persistence. And then where you want to use the rest of the stack, you use that. When you don't want, you don't have to. So it's quite flexible. Any more questions? Yeah?
Is the database fully ACID compliant?
Yes. So it's fully ACID compliant. So, well, you can decide if you like wait for the data to be persisted, because sometimes it's a valid compromise to do it asynchronously, so you don't really wait for the data to be stored on the disk. But by default, you wait for that, and you have a snapshot isolation between the transactions. And also, optimistic concurrency control, I think it's worth to mention here. So we assume that there is no actual conflict. Then if there is a conflict, you restart the transaction, but you don't check, as in the pessimistic concurrency control, if any other transaction touches different objects. Yeah, one more?
Sorry, I just have so like coming from, for example, a JSF background, I feel like there's probably some Java developers in here. You know, when I've been on some projects where they were using prime faces, and then they were building some of their own components, and then like kind of slowly migrating away from that, it seemed like there were always issues with the packaging because of the other JavaScript libraries that were being included in. So you ran into, oh, we have two different versions of jQuery on this page, and we have. So how does your framework help you deal with that? Because that seems like the biggest barrier to the componentized web, which is great, but it.
Well, so basically we used all new developments by web platforms. So we are not trying to develop our own way of doing web. We just are based on the pure web standards. So Shadow DOM and custom elements are a way of doing that. So there are like still some leaks between the layers, but everything goes towards that direction. So hopefully very soon it will not be a problem anymore to load two jQueries in the same page. But it's not like that yet. Yeah. Yeah.
So so if you have 5 different apps, and are you writing also a 6th wrapper app, or is one of the apps in charge of wrapping it? Who's maintaining that in your design?
What do you mean by wrapper app in that context?
Well, you've got
Like the page.
you had each of the you had each of the separate apps, right? But they were being self-contained and told, hey, you're going to be over here, you're going to be here, you're going to be there. Who's what's?
Yeah. So basically, like by default, developers to the views that they create, they describe some rules that say that, hey, if anybody has something to say about a person, please give me the interface of that. So then if you ask for the one application, you make a request to the one application, but other applications know something about the same concept in the database, they also contribute with their interface. And then you can choose, when you're composing that solution, what to accept and what to delete. So there is some special utility application called Blending Editor that helps you to deal with that and store that, what we call composition. So if you want to have less on the screen, then you remove parts. If you add something manually from different applications, you can specify that, hey, on that page, I would also like to load that request with these parameters.
And where is that composition stored? Is that
it's stored in the database. So,
okay.
And then you can export that and deploy that with your set of applications. Okay, so I think that now it's a good time for a beer. Thank you.